Okay, so today we're going to be talking about blood and artificial heart technologies. My name's Nick Bidwell.
Ian Brocious.
Sam Bitzer. So the artificial heart valve history. The first artificial heart valve was installed into the human body in 1952. Mechanical heart valves gained in popularity, with the first one being used in 1960. Today, over 40,000 people live with mechanical heart valves. Artificial tissue valves rose to popularity after the mechanical valve. So the fluid mechanics of the heart valves. Non-physiological blood flow is a large complication with artificial heart valves, meaning that the blood doesn't flow the way it normally would. Mechanical heart valves require the use of blood thinner medication, whereas tissue valves do not. Mechanical valves require the use of a leaflet, which opens and closes with the beating of the heart and allows for hemodynamic blood flow. Tissue valves may also use leaflets.
Okay, next we'll be talking about blood flow dynamics of the heart. Quick overview: blood is received from the right atrium, then passes to the right ventricle. Blood is then pumped up to the lungs via right pulmonary vein. Then the oxygenated blood is then received by the left atrium, then passes to the left ventricle. And then finally, left ventricle pumps blood in circulation. The left ventricle has to pump about 13 kilopascals to pump about 5 liters of blood into circulation. Blood flow dynamics of arteries. Arteries carry blood throughout the body. They eventually reach the capillary system, which is small vessels. Length and diameter are taken into account when calculating the pressure in an artery. Blockage causes flow of the blood in arteries to become in an unsteady state. And veins carries blood back to the heart, and the pressure in the veins is lower than that in the artery because the thickness of a vein. Thickness of a vein is not as thick as the artery. That's good.
So the materials used in artificial valves. For the mechanical valve, they use metal alloys, which are most likely titanium or stainless steel. They also use pyrolytic carbon materials, and Dacron and Teflon are used for the suturing because these are the most biocompatible materials available. So for the artificial tissue valves, pig's heart, which is most similar to the human heart, is used. And they use a xenograft to place the tissue in the heart. Biological leaflets made from either a cow or a horse's pericardial sac. So this is a picture of the internal anatomy of the heart compared to the internal anatomy of the pig heart, which shows that there's many similar things, such as the atrium.
Alright, next we'll talk about mathematical blood flow model. Two equations that's used is the Navier-Stokes equation and continuity equation. Blood flow is assumed to be steady, and blood considered a Newtonian fluid is the two assumptions we make. Equation provides a computer plot which displays the flow of blood through the heart valves. And here is a picture of the Navier-Stokes equation. Rho is the density of fluid, V is the viscosity of the fluid, P is the pressure at the point, and F is any external forces acting on the fluid. Mechanical systems, the APO 900 cardiovascular system was approved in 2018, monitors the mitral valve, and provides four-dimensional orthostatic echo and transesophageal echo of the valve. And the Lessendo 880 more generalized system provides echo imaging and vector flow mapping of the blood within all valves of the heart.
So the Bjork-Scheele convexo-concave design was considered a failure, and it appealed to the ethical issues within the surgical process. Doctors were at first unaware of the possibility of strut fracture when they installed the mechanical devices into the patients. After Bjork-Shiley realized that strut fracture was a possibility, they sent letters out to the doctors, but they did not send letters to the patients with the heart valves already installed. They feared that anxiety over the issue would cause stress and cause a failure on its own, and this appealed to many ethical issues with designing.
So next we're going to talk about blood vessel stents. What they are is they're a small mesh tube that are used to support weak or narrow arteries, and they're used in percutaneous coronary intervention to restore blood flow. They're used to treat coronary heart disease, and they can be used in blood vessels all throughout the body. And how they work is they are inserted with a balloon and a mesh design, and then they're expanded in the artery to restore the flow. Now we're going to talk about the heart and lung machine. This also is called the cardiopulmonary bypass. And what it does is it allows for a bridge, or basically keeping a person alive between heart failure and transplant, and then it's also used in a lot of different surgery applications. And the way it works is it bypasses the heart by bringing blood into the machine, and it is then oxygenated, and then it's pumped back into the body so that it can be restored throughout. Now we're going to talk about artificial hearts. The Jarvik heart is an example of a mechanical heart that is an application. It's not a fully mechanical heart, but what it is, it's a pump that acts as a booster pump to the heart. So it has a control system that's external that the patient sets based on the amount of activity they are experiencing. And what it does is it boosts the amount of blood flowing from the left ventricle to the aorta in order to make sure that the proper amount is flowing during different activities. And the first artificial heart that was used in clinical applications was in 1982 at the University of Utah, and that patient was able to live 112 days with the first application. So in the future, the goal is to eventually create an artificial heart technology that is self-contained, meaning that there's no external pieces or parts to it. There also is a hope that there needs to be no human interaction so that there's no cause of harm from a person doing something wrong. We also want it to be a permanent solution to heart failure, and so instead of having to transplant or using it as a bridge between transplant and failure, it'll just be a permanent fix. And the goal is to have no more transplants that need to be done in the future.